So in the previous video, we discussed about the concept of ensembles, and we know that you must have studied concept of ensembles already in BSc, that there are three kinds of ensembles, right? So first is micro-canonical, second canonical, third grand canonical ensemble. So in this video, I will dot down some of the main characteristics of the micro of the three kinds of ensembles. First one was the micro canonical ensemble. So here you have NVE constant. NVE as constant. That means number of particles, volume, energy are all constant. So what is the macro state of this microcanonical ensemble? It is the NVE. So that represents the macro state. Since I don't allow the number of particles to change or the walls of the elements to move, and I do want to keep the energy constant, which means that basically I am excluding myself from all the disturbances for every element of that. So I can write down the characteristic as it is made of rigid, impermeable, adiabatic walls. So how do you draw that? I will draw like this. Okay. So what does this red thing comes represent? It comes the thermally insulated walls, which means I don't allow the energy to the temperature to get into the system, or I don't allow the energy to change inside. But here, what do I allow? Between within an element, within say this element, I do allow the quantum state of each particle to change. So within each element, particles is allowed to change. That means this is what? Not the normal E. I can tell that this is Roman E. Whatever it is, epsilon. I don't call it epsilon, but yeah, Roman E. So the EI. So within this element, right? So there are a lot of particles, and you can the picture you can make a you can think about the system like this. There are a lot of particles, and there could be different energy levels, for example, and at different instance of time there will be different number of particles in each levels. That means my small ei of the system or within the system, within the element, will be varying. For example, if it's at some point of time, if it is 322 is the configuration, at some other point of time, it could be 223, right? Or 142, whatever it is. So that is how. So I can write it like N V EI. N V EI. So this is epsilon I. Okay. So let's not have confusion with E. So this is NV epsilon I, NV epsilon I, NV epsilon I. So this is how I do represent a microcanonical ensemble, and these three are its characteristics. The second one we have already told over here. This is the, what is that? This is the canonical ensemble. We know it. We have explained that in detail. So let me just dot it and mention the main characteristics. Sorry, I should write canonical ensemble. So canonical ensembles, 1 NVT is constant. NVT is the constant, so that defines the macro state, and internal energy is to vary, right? Internal energy is allowed to vary, which means that my the vary between the elements, if you want to write it full, right? That is why we have wrote down here NVEI, NVEI, NVEI. And the internal energy of the system is allowed to vary, whereas the NVT is a constant. Right. And the third characteristic could be they are rigid walls, volume is constant, and they are impermeable walls. And we already discussed this point. All these blue walls over here, these walls, they do allow the temperature to participate in the state of the element. So they are placed in a heat bath so that all the elements within this system gets the same temperature. So these walls are basically diathermic walls. So diathermic walls to ensure uniform, constant temperature, but they do not allow a temperature getting into the system, the system of elements from outside. So it is prevented with the help of a thermally insulated grand wall. Okay, and I'm not drawing the figure here because you have the figure already in the other one, right? Already in the previous video. So the third one is called the microcanonical ensemble. So the microcanonical, sorry, I was thinking something else. So what is it called? The grand canonical ensemble. Grand canonical ensembles. So here we have mu Vt constant, whereas mu is the chemical potential. So the mu Vt will be constant here. Between the elements, number of particles and the internal energy can vary. Okay, so between the elements, number of particles and the internal energy can vary, which means that I do allow the particles to exchange between the elements and also the internal energy EI. So how do I put the diagram, right? So naturally all my systems, all my elements should be protected by a thermally insulated wall right, and I construct the systems inside. It has to allow the particles also to be exchanged between the elements, right? So I represent the permeable walls by broken lines like this. And what do I write inside? I will just keep my writing Ni V Ei. Ni V Ei. So that is their microstates, Ni V Ei. And of course, this is thermally insulated wall. This is the heat bath, so that I allow the energy to be exchanged through this heat bath. Right. So this is how I represent a grand canonical ensemble. So as the third point I can write, right, UVT is equal to constant between the elements, number of particles and internal energy can vary. And also third the third point, which is about the walls. They are rigid walls because I don't allow the volume to change. So they are rigid walls with permeability to allow mass and energy exchange. So that is it. So that is how I represent the grand canonical ensemble. So if you remember, so this is an artificial construct where at one instant of time itself I get the picture, a whole picture of the statistical distribution of the system in terms of its micro state. But definitely, so this one ensemble is defined by its macro state. And this theoretical concept, which is proposed by Gibbs, is very important and useful for our discussions on the statistical mechanics.